globular head. There are 4 important regions on the myosin head. Keep in mind that we're dealing with amino acids in various folding geometric folds. So, first, one area is the actin binding site. On the myosin head. That's the location which can interact with the myosin binding sites and actin. If they can get together. If they get together, that's called a cross bridge. When a myosin head gets together with actin, that's called a cross bridge. Another site on the myosin head that's very, very important is an ATP binding site. By the way, for just modeling this, we don't really know exactly where these are on the myosin head. Three-dimensional. But they're somewhere. Now, if ATP is bonded to that site, this will break down. This relationship ends if ATP binds to that site. That's called uncoupling of the cross bridge. So as long as ATP is not on that site, the myosin head might be able to interact. But if ATP gets on the myosin head, then whatever interaction was occurring ends, and the two compounds uncouple. Another binding site is an ADP binding site. Adenosine diphosphate. Now, these two binding sites for these two nucleotides cannot be occupied at the same time, because the myosin head changes shape when one or the other is present, and it restricts access to the opposite one. So only one type of nucleotide can be bonded to its binding site at any one time. Now, if you don't have ATP, but you do have ADP on the binding site, and you remove it, if the ADP comes off, the myosin head moves like that, like your wrist. Removal of the ADP causes the myosin head to spring forward. It's called activity, or power surge. And there's one more very important component that we're going to talk about. Part of the myosin head is ATPase, an enzyme, which causes the ATP that might be on the binding site to be catabolized into ADP, which will move on to its binding site. Okay, so there are 4 important components of the myosin head: an actin binding site, an ATP binding site, an ADP binding site, and the ATPase enzyme. However, this enzyme is very special. By itself, it's not active. If you want this enzyme to be able to catabolize, convert ATP to ADP, you have to add calcium. It's a calcium-dependent ATPase. calcium is a coenzyme for this particular ATPase. So you don't have that everywhere. This is one of the few places you have a calcium-dependent ATPase. In other places, ATPase is active by itself, and not in the sarcoplasm. So this is the second role of calcium. The first role is to cause the tropomyosin complex to shift position, change its shape, so that it exposes the binding site on actin for myosin. And then on the myosin head, it activates ATPase. Now, here's another thing you need to know about myosin. In the sarcomere, as shown here, there are bundles of myosin that form the A band. This is really the A band. This is the M line. This is the H zone. But the myosin heads on one side of the sarcomere are pointing in one direction, and they would move this way. The myosin heads on the other side pointing this way, and they would move this way. The myosin heads would move toward the M line from both directions. So that's very important because when they relate to actin, they're going to pull the actin from both directions. And that's going to pull the V lines closer and closer together. And the actin is going to slide over the myosin. The myosin is stationary, only the actin moves. And so that's why in these illustrations, you see these little teeth here, little projections. They represent the direction of the myosin head. Right? And they're going to move toward the midline, toward the M line. That's going to grab actin from both sides and pull it towards the M line. And that's going to pull the V lines closer together. The I bands are going to get smaller, and the H zone is going to get smaller as the actin moves toward the M line. And that phenomenon is called the sliding filament theory. So we can see how it works molecularly.